Okay, thank you very much. Thank you for coming for this presentation and actually both sessions. And the topic of my slides is related to add paths in a sense that I'm not going to talk about overview of add paths. That comes later. Dave will do an excellent job. I'm going to talk about deployment cases where you can see if add paths is a must or not. So the objective here is to discuss the most burning features you may have today, why you may require to distribute more than best path in BGP. Those are load balancing, fast connectivity restoration, as well as the 3107 cases. I'll try not to talk too much about the 3107, but just for those of you who require, who think they require add paths for 3107, I'll have a slide discussing the alternatives as well. And the most important point is that it's not really the problem of new protocol extension in BGP, or that you have to upgrade your entire network to support add paths. Really, the problem is with add paths that it's increasing your BGP states in all the routers. And that's really something we should be looking seriously at as far as being very careful if we have to really increase number of BGP paths in all the routers in the domain. So I'll go through the couple of scenarios for IPv4, IPv6 networks. Then I'll present basically how they look like with and without add path, and show some alternative to add paths, which is basically a mechanism to distribute more than best path in BGP without actually requiring to upgrade both sides of BGP speakers. As I mentioned, there's going to be some discussion about the redundancy in 3107, load balancing in 3107 networks, as well as I finish up, if the time allows, with the illustration how to achieve scaling in the growing internet table size. This topic is not really about any of the VPNs. I know that some people may require distribution of more than best path for VPNs, but this is out of scope of this talk. You can easily make a different RD. You can even renumber the RD on the RRs if you have the ASBR redundancy issue. So this is not the talk about the VPN cases. And if you expect this to be a little bash of MPLS, I will not let you down. So the typical ISP design originally evolved based on the hierarchical IGP models. First, we had OSPF with Area 0 and areas around Area 0. Then we had ISIS doing L2, L1s. So the original networks, if I remember, from 96 and around that area of time, looked like particularly this. So you had basically POPs and the core. You have ABRs acting as RRs in your data plane. You have fully meshed RRs in the core. And at that time, nobody really was thinking about advertising next hops into your IGP end-to-end, because it was not really required. BGP convergence was good enough to satisfy the applications of that time. So what is exactly changing with the time that now we are looking at different ways to distribute BGP information? I mean, primarily, the new applications came and require sub-second convergence. And that's what we have to keep in mind. Load balancing, I think, is also important to equally utilize your internal or external links. But that's, I think, the secondary objective. And if you look at this picture, what is really missing, it is just the use of new tools like best external or next hop self. Next hop self is nothing new. It has been there forever. Best external, it's a new tool which is available today in most of the implementations and allows you to distribute your external path, external to a domain or external to the cluster. It also works across the confederations, but I will skip that third option for now. So what what is really important to keep in mind is that if you use the best external on the edge, as well as on the route reflectors connecting between the POP and the core, you really gain a lot of information which is being distributed by BGP. And my point of this entire presentation is to illustrate that this information which you will get through the best external is sufficient enough to address most of the needs of current networks. I also discussed how we can use add paths in this model down the road. So the best external here works on two different levels. One is the AS best external, which you enable on the ASBRs or the PEs, which basically allows you to advertise eBGP learned path, even if overall best path is IBGP. It can be due to local preference setting or MED settings. So normally, when the IBGP path wins and you have advertised the external path, you withdraw the external path. With the best external enabled, you don't. And the second place you can enable best external is on the cluster boundaries between your route reflectors, between the POP and the core. And in this case, what is happening that you are advertising the cluster domain external path. What is really cluster domain is cluster domain in RR, it's RR in its clients. So if the overall best path is on the client side, you advertise the path received from the other clusters, from other RRs, and vice versa. In both cases, in the POP and in the core, you have the full mesh. So now let's walk through three scenarios, slowly moving from the current model in scenario A, with the leaking of next hop's information from the POP to the core in scenario B. And then in scenario C, I'll illustrate the benefits you'll get by using both the next hop advertisements in IGP, as well as the best external on the edges, as well as on the POP to core boundary. So with scenario A, what you have basically, you have 4 POPs. You have 3 external connectivity from POP 1, you get path 1. From POP 2, you get path 2. And from POP 3, you get 2 other paths. I call it 3A and 3B. And that's the current model when you don't enable any new functionality. So what you get in this model, then if your path number 1 goes away, which is the best path, it requires time for BGP to withdraw the path and then for RR2 and RR3 to advertise new path to a given prefix. That takes time. And that's what basically people complain about, because it is not that BGP is slow. The BGP in this picture has to handle all prefixes. So most likely close to 500,000 very soon. That's what causes the delay in propagation of the information. If you just modify this picture with advertisement of the next hop reachability information between the POP and the core, you get automatically the benefit of fast convergence on those route reflectors which have redundant paths. They have redundant paths because you enable best external in the POP routers, in the ASBRs. So in this particular picture, we don't enable best external on the POP to core boundary yet. We're just advertising the next hop reachability or next hop down event, in fact, in the IGP, what causes the RR2 and RR3 to invalidate the path which is basically wrong and calculate the new best path. In the same time, you can have PIC. PIC is prefix-independent convergence. So on those RRs, being ABRs in the data plane, you can actually very quickly, with one single trigger of the message, switch over your forwarding path to a valid path. And that is, I think, very important message, that just by sending this information, you already get sub-second convergence when you can. Not everywhere. You will not get it in the POP 4, because there is no redundant paths there yet. But that's the first step. And what is really here happening, with one single message of the IGP, you are invalidating all 500,000 BGP paths. That is the most important observation to remember from this slide. We used to have in BGP the idea which was called the weapons of mass destruction. Worked together with Dave on that, and it basically caused one BGP message to do the same, to invalidate all paths received over some peering link. But it turned out to be that you can achieve the same functionality with flooding a next hop in IGP, so we kind of gave up on that idea altogether. So let's move on and let's observe the scenario C. Scenario C is what we had in scenario B, plus enabling best external on the POP to core boundary. So now you can see that just by using basically this configuration, which is local to the RRs, you get all the paths which are required in all POP to core boundaries. That means that you can really quickly switch over your data packets, both the packets in flight or as well as the new packets, to an alternative exit point out of your network. And there is no need to upgrade the ASBR SPEs. Those ASBR SPEs just keep a single best path because you still go through the ABRs, which are in the data plane. So ABRs are very quickly converging to a backup paths. They can do load balancing as well. And the convergence, the connectivity restoration here, it's almost ideal. You don't want, you cannot expect any better, even if you do, if you flood the paths everywhere. So now let's discuss a couple of sub-options of this model. How to handle the next hops. So the basic model is not to change next hop, both on the ingress to your network, as well as when you distribute the paths through the network. And that works very well, provided that your IGP reachability of the next hop goes between the POP and the core. At the core to the POP, you normally do the summarization in the IGP. And this model is what I call the C1 model, which works, which is currently here marked in green, which illustrates that the next hop is unchanged throughout the domain. You don't have to basically do any modifications on the next hop. And that's, in my opinion, the most recommended model to deploy. The C2, on the other hand, it's a model in blue where, for some reason, perhaps you want to do domain-wide flooding of next hops. For example, you use the same next hop for your MPLS LSPs and for your IPv4, IPv6 routing. Of course, you can have alternative not to use the same next hop, but just in case you do, the only change you would have to do is to change next hop self on the core to POP boundary. And still all the connectivity restoration properties or the load balancing works without changes. A special case I call the C3 is, I think this is not so much often case, but you may have a case where all of your exit points out of the network are from the same POP. In this case, what you do actually, you virtualize the exit points on the POP boundary by setting next hop self between the exit POP, top 3 in this case, and the core. But the alternative, of course, is to split your eBGP peering to be connected to a different POPs. And that's, I think, in my opinion, the recommended way to build the IGP network and your AS. So it was fine till basically the day we had MPLS coming. MPLS coming was basically, in my opinion, gained some popularity just because the routers at that time didn't do very good IP encapsulation. Now it's not the case. Now most of the modern routers from many vendors do very good IP encapsulation, so you can run pretty much all of your nice services over IP encapsulation. But the point here is that the arrival of MPLS made the network flat. And it was done for 2 reasons. First of all, LDP have to have exact match with the advertisement in the LDP to advertisement in the IGP. So for all practical reasons, if you wanted to map a traffic to an LSP, it was pretty much /32s end-to-end. Otherwise, your application break. With TE, it's even more interesting, because in TE, you don't only have the exact match, but you also have to have extensions to IGP to carry leak bandwidth, which is just a control plane information. It's not, nothing really in TE gets reserved at the interface level. It's only control plane reservation. In any case, to do inter-area TE, it's already an adventure. I don't know if anyone really in production is using the inter-area TE today. Some concept of the PCEs were introduced, but it's not really an elegant way. So the flat network was really the model. And then people started to have discussions how big my IGP can be. If 500 is enough, if ISIS can handle 5,000, and so on. And that's pretty much why we see a lot of networks which didn't use one network for IP and other network for VPNs, which will merge into the one, have been designed in the flat model. Some networks were spanning continents with 3 ASs and still running flat ISIS. And that's what was really required to support the applications. Some people still use the services over IP model with the hierarchy, and they are still operating just fine. Some of them are in the room here. But on top of this, we have to have still the case of fast connectivity restoration and load balancing. So if you see basically what is the analogy to our C1, C2 case in this network, is basically to distribute all paths to all the edge of the network. So the more paths you distribute, the more states are being kept all over the network as far as BGP is concerned. Of course, you have to also do the upgrade before you distribute all the paths. And if you really don't have LSPs and you have flat model, then you have to distribute the paths also to the core routers, the same way as you distribute to the edge. So unless you have a tunnel using flooding add paths network-wide, it's really a stretch, in my opinion. In fact, this picture just shows single path. Of course, you have double that because you peer to do different RRs, the most likely, for redundancy reasons. So as you can see in this one, the amount of control plane information explodes because it's all flat. So now the questions also are coming. Let's assume we have add paths in place, but how many paths to distribute? Is it only second path enough? Or should we distribute n paths? Maybe we should distribute all paths. And there are many research projects currently going to actually find out what number of paths is the optimal number of paths to be distributed. It's not an answered question because it really depends on the application, on the capacity of the network, and so on. Just add paths itself, it is nothing fancy. Encoding-wise, I don't think it's any wrong, but it's not the encoding which is something to worry about. For IPv4 NLRI or for 3107 NLRI, it is basically virtualizing the path by adding the path ID. Previously, in the router, you kept the advertisement state on a prefix basis. Now, when you use add paths, you have to keep it on the per path basis to know which paths you are sending to which particular peer. So it increases the amount of memory router keeps, but this is not so of an issue. Now there is an alternative solution to distributing more than a best path. Imagine the case where, for example, for your application, you want to send a second best path, just, for example, for fast convergence, for fast connectivity restoration. So if I introduce a route reflector, which I will instruct to select second best and advertise second best to my client, I don't need to touch the client. Client only requires to be establish a new IBGP session to this shadow RR, and the new path will come from the shadow RR, the path number 2 in this particular case. So this actually requires only introduction of the new code on the route reflector. If you talk to your favorite vendor, this solution may be coming to you soon, if it's useful. There is a draft in IETF in the GROW I have for this particular solution. It doesn't change this protocol of BGP. It is just uses the observation that if I send a path on the new BGP session, iBGP session, it is kept and it can be used in the router without, just like it will be coming on the same iBGP session. So if you, for example, don't want to use the full iBGP mesh within the core or within the POP, you can use this solution to actually advertise more than best path to your iBGP clients. And this is just an example of using 3 of those diverse path RRs. Second one is calculating the second best. The third one is calculating the third best. I don't know for all practical purposes if we need to have 4 and 5 distributed. I think if you just do the second best, it's more than enough for most of the applications. I think this is what I was talking. Okay. So now let's move back to the MPLS networks, and let's illustrate how the MPLS networks scale, or what the vendors are now telling you to how to scale the MPLS network. So we come back to the flat model, and it is a good model for the medium-sized network. If the network grows, becomes large, or extra large, or extra large, then it is really a challenge to keep growing your IGP, even just for the /32s. Forget about connected interface addresses to the number of 10,000, 30,000 PEs. And these are some real numbers we have been approached by customers to address. So what is the answer to these challenges? The answer is to move back your flat MPLS domains to hierarchical model, just because there is no other way to scale the IGP. And the answer is to run LDP within each POP and interconnect the POPs through 3107. So it is extremely close analogy to what we have just been talking about in the model of the hierarchical ISP network. I don't want to go into details how is it done, but just for your information how to build 3107 network without AdPath, I have one illustration for your reference here, that if you observe the fact that the 3107 in this network is carrying /32s of your peers' domains, because you don't want to distribute those into your IGP, you can apply the same exact C model to your 3107 MPLS domain, and by setting next hop on the RRs, which are ABRs in the data plane, you can achieve the same scaling, again, without the need to push all the paths to the edges. That's just a configuration thing for you to execute on. It doesn't require anything else than just configure the network in such a way like presented here. So what are the conclusions so far? As you see, the traditional ISP model, it's quite good, because even large-scale MPLS networks are coming back to using this. You can, of course, use pure IP encapsulation for many of your services, I would say all services, and it's still fine to use the hierarchy in the IGP. The key message, which I would like to have you walk out of this room with, is that you can achieve really strong network. You can build really strong network with the fast connectivity restoration, with making sure that your BGP paths are virtualized on the POP to core boundary. And that's what we are trying to basically propose, what I'm trying to propose in this slide. Diverse path distribution can be used equally well to address some of the cases where you really need to distribute more than best path between the clients. You don't want to fully mesh the clients directly. Just a side note for those of you who run 2547, that the model of hierarchical design could be very nicely applicable also to your VPN routes. You can have the VPN routes on the ABRs doing option B. And if you add the RT constraint on top of this, it's really giving you very nice scaling properties. But that's totally a little comment in the fine print. So now let's have one more slide talking about another benefit of having the network to be hierarchical. When the number of internet entries grows, perhaps to millions, especially when you are talking about reselling of lower than /24s between people when the IPv4 exhaustion is really seen, you may see the increase in the size of the V4, V6 table. So what happens when your edge routers cannot keep up with that size? You go to your vendor and pay the money. Or you configure your network in such a way then you don't put into the fib all the entries, but just a default entry to the ABRs. In the control plane, you still have all the BGP routes. But what really is the bottleneck is the fib space on the line cards in most cases, especially when you're talking about millions of routes to be carried. So this is the model which automatically, when you have in place, allows you to inject into the fib default route or some group of routes to point you to the ABRs. And there is ongoing work in this. It is called the virtual aggregation work. And Paul Francis is leading the work in the growth working group in the IETF. But the point of this slide is that with the same design as we discussed before, you can have also a case which is applicable to scaling the routing table size. So the final conclusions. Add paths is just a way to flood BGP information. Diverse path is also a way to flood it, to advertise to a client without upgrade of the client. But it's not the point. In my opinion, the really problem is to flood edge to edge so massive amount of information. And I would like you to think about doing that twice before you do it, because there is alternatives available by the given design. And if you basically make your network in a hierarchy and virtualize the BGP paths, you get the same application benefits as you perhaps originally thought of having when you think about add paths. My many thanks to a lot of people who contributed to this work and reviewed it for me. And there is some reference page. As you can see, there is nothing proprietary in this particular slides. These are all standard drafts in the IETF, which I'm using here as the tools to achieve fast connectivity restoration and load balancing. Also, I didn't tell it originally, but if you have the full mesh of all RRs carrying all the paths, you also address the oscillations case. So it's also maybe one of the issues in your networks today. So if you have any questions, I know Randy has one, please ask now, ask offline. This space in the FTP engineering URL will be available. I will add some more information there as well when we continue the work on the solutions here. Randy, please.
Actually, I don't, if it's okay, we'd like to try to have both presenters go and then hold questions to the end and then have your way.